In this video, we want to compare the two methods of evaluating cross product of two vectors. The first method is direct calculation from the definition of cross product itself. And method number two is the determinant method. To begin, let's first review the cross product of two vectors. Assume that you have two vectors on a plane, vectors A and B. Now the cross product of vector A and B is given by A cross B equals C, where C is the resulting vector of the cross product between A and B. The direction of the vector C is perpendicular to the plane containing vectors A and B, and the direction is downward as determined by the right-hand rule that we discussed in the previous video. The magnitude of this cross product, that is the magnitude of vector C, is given by the following. Magnitude of vector C equals magnitude of vector A times the magnitude of vector B times the sine of the angle between vector A and vector B. Next, from the definition of the vector product just outlined, let us write down vector products involving unit vectors I hat, j hat, and k hat. First, I hat cross j hat equals k hat. Next, j hat cross k hat equals I hat, and k hat cross I hat equals j hat. Now we can reverse the order. J hat cross I hat equals minus k hat. K hat cross j hat equals minus I hat. I hat cross k hat equals minus j hat. And the last three, I hat cross I hat equals to 0, or null vector, because cross product of two parallel vectors will be 0. Now likewise, j hat cross j hat equals 0. K hat cross k hat equals 0. We would like to point out that everything we have outlined here had been explained more fully in a previous video on cross product. So if you have not watched that video yet, please refer to that video to get a fuller picture of what has been said on the slide. These results of cross products involving unit vectors are very crucial, and we have to refer to them when we calculate cross product between generic vectors using the direct calculation method. So let's get started with the direct calculation method. Suppose you're given two vectors, vector A and B. Now each are written in terms of unit vectors, I hat, j hat, k hat, along with their components ax, ay, az, and bx, by, bz respectively. So how do we calculate A cross B? So we will multiply term by term. So first, axi hat, so I hat cross I hat, that is 0. Next, axi hat and by j hat, so I hat cross j hat, that's k hat, so it's going to give you a x by k hat, and then axi hat with bz k hat, that's going to give you I hat cross k hat, which is minus j hat, so together with the coefficients it's minus ax bz j hat. Now let's do the second term, ayj hat bx I hat. So j hat cross I hat is minus k hat. So together they'll give you minus ay bx k hat. And then ayj hat and byj hat is j hat cross j hat. That's going to be 0. And then ayj hat and bzk hat, j hat cross k hat is I hat. So together it's going to be ay bz I hat. Repeating for the azk hat and bx I hat. K cross I is j, so that's going to give you az bx j hat. Then azk hat byj hat, k hat cross j hat is minus I hat, so together it's minus az by I hat. And finally azk hat and bzk hat, k hat cross k hat is 0. So grouping all these 6 non-zero terms, we get the following. The x component of the result is ay bz minus az by, and then the y component of the result is az bx minus ax bz, and the z or the z component of this cross product is ax by minus ay bx. So this is the full result for the cross product of vectors a and b using the direct calculation method. Now let's do this same cross product using the determinant method. In the determinant method, we write down the components of vector a on the top row and the components of vector b in the bottom row. The reason is because a appears as the first vector in the cross product and b appears as the second vector in the cross product. So the order of the vectors matter here. So let's go ahead and obtain the x component of this cross product. To get the x component, you cross out the I hat in 2 mutually perpendicular directions. That will leave you with 4 numbers, ax, az, by, and bz. And you can treat this as a 2 by 2 determinant, and you calculate like you would calculate a 2 by 2 determinant. That is ay times bz minus by times az. And that's going to be ay bz minus az by. Next, the y component. So we write a minus j hat. Note that we are putting a minus here. It's part of the formalism. And you cross out j hat in 2 mutually perpendicular directions. That would leave you with ax, az, bx, and bz. And now you proceed as if you're calculating a 2 by 2 determinant. That is ax times bz minus bx times az. So ax bz minus az bx. And finally the z component. We cross out the k hat in 2 mutually perpendicular directions, and that would leave us with these 4 numbers, and we can treat them as determinant, a 2 by 2 determinant, and we can proceed as if we are calculating a 2 by 2 determinant. That is ax times by minus bx times ay. So it's going to be ax by minus ay bx. So it doesn't matter whether it's ay bx or bx ay, because they are just scalars, they're just numbers. You see that the result obtained here from the determinant method matches the result obtained here from the direct calculation method. They are identical. As a further illustration, let's look at the following numerical example. So you have two vectors, minus I hat plus k hat, and 2i hat minus j hat minus 4k hat, and we want to calculate the cross product of these two vectors. So let's proceed term by term. Now first, I hat cross I hat, that's going to be 0. Next, I hat j hat, that is k hat, but you have a minus, and then minus becomes positive 1, so that means you just have k hat there. And then you have minus I hat with minus 4k hat. So I hat cross k hat is minus j hat. But you have minus 1 and minus 4, so that is 4. 4 times minus j hat is minus 4j hat. Let's proceed with the second term. Now k hat and I hat. So k hat cross I hat is j hat. You have 1 here, and you have 2 here, so that's 2j hat. Next, k hat and j hat. K hat cross j hat is minus I hat. You have 1 here, and then you have minus 1 here, so together is minus 1. So minus 1 times minus I hat is I hat. And finally, k cross k is 0. So the final answer to this cross product is I hat plus 2j hat minus 4j hat plus k hat, which is I hat minus 2j hat plus k hat. So that's the answer to this cross product. Now let's do the same cross product using the determinant method. Let's first calculate the x component of this cross product. So to get the x component, we cross out the I hat in two mutually perpendicular directions. That would leave us with 0, 1, minus 1, minus 4. Now we proceed as if we are calculating a 2 by 2 determinant. So 0 times minus 4, that is 0, minus 1 times 1, that is minus 1. So it's going to be 0 minus 1. Now the y component, do not forget the minus sign that we need to place here in front of that j hat. So we proceed as before, crossing out the j hat in two mutually perpendicular directions. That would leave you with minus 1, 1, 2, and minus 4. Now we proceed as if we are calculating a 2 by 2 determinant. So that is minus 1 times minus 4, so that is 4. Minus 2 times 1, so that is 2. And finally the z component, k hat. We cross out the k hat like that, and you're left with these four numbers, minus 1, 0, 2, minus 1. So you proceed like you're calculating a 2 by 2 determinant. So that is minus 1 times minus 1, so that's 1, minus 2 times 0, so that is 0. So the final answer is I hat minus 2j hat plus k hat, which is exactly the answer that we obtained earlier using the direct calculation method. It appears that direct calculation of a cross product from its definition is more fundamental in its approach than the determinant method. It may even appear that the determinant method arises from the effort to recast the direct calculation result of a cross product in a determinant form, thus making the process of calculating cross products more convenient without having the need to remember cross product results between unit vectors.